Every hydraulic routing method you use comes back to one set of equations, the one-dimensional Saint-Venant equations. They are the foundation of hydraulic modeling, yet in practice we rarely solve them in their full form. In this video we will break down each term of the Saint-Venant equations and explain what it physically represents. More importantly, we will explore what happens when we keep or remove each term and how those simplifications lead to the routing methods we use every day. Let's get started. The Saint-Venant equations are named after a French mechanician who derived them in the late 19th century. These equations represent the application of the conservation laws of physics, specifically mass and momentum, to the one-dimensional flow of an incompressible fluid. It serves as the parent theory from which all standard hydraulic routing models are derived. The Saint-Venant equations presume a control volume of length partial x along the channel axis. The fundamental assumptions in these equations are as follows. First, the one-dimensionality. The transverse and vertical velocity components are considered negligible relative to the longitudinal velocity. This implies that the water surface is horizontal across any cross-section, a condition that holds for narrow channels but may fail in wide floodplains or around sharp bends. The second is hydrostatic pressure distribution. The vertical acceleration of fluid particles is assumed to be negligible compared to gravitational acceleration g. Consequently, the pressure distribution along the vertical axis is hydrostatic, given by this equation. This shallow water assumption is valid only when the wavelength of the flow disturbance is much larger than the flow depth. It breaks down in regions of high streamline curvature, such as flow over a weir, through a sharp contraction, or within a hydraulic jump where vertical accelerations are significant. The third is the small bed slope. The channel bed slope snot is assumed to be small enough that the following approximations become valid. This simplifies the geometry, allowing the flow depth to be measured vertically rather than normal to the bed. For slopes greater than approximately 10% or 6 degrees, this assumption introduces error, and the pressure term requires correction factors. The fourth one is the steady-state friction approximation. Perhaps the most empirical assumption is that the shear stress at the channel boundary in on a steady flow can be approximated by relations derived by the steady uniform flow. This justifies the use of Manning's equation to calculate the energy loss slope SF. While generally accepted, this assumption ignores the effects of unsteadiness on the turbulent boundary layer structure. The last one is incompressibility. The density of water rho is presumed constant, and the channel bed is also assumed to be fixed. Therefore, no erosion or deposition is modeled in the pure hydraulic equations. Now let's explore the Saint-Venant equations. The first component is the continuity or conservation of mass equation. The principle of mass conservation states that the rate of change of mass within a control volume must equal the net mass flux across its boundaries plus any source terms. For an incompressible fluid, this reduces to a volume balance. The differential form of the continuity equation is like this. The second component is the momentum equation or conservation of momentum. The momentum equation is the application of Newton's second law to the fluid element. It balances the rate of change of momentum with the sum of external forces, gravity, pressure, and friction. The conservation form of the momentum equation is like this. For analysis, it is often more instructive to use the non-conservative form expressed in terms of velocity and depth. Dividing by GA, this equation yields this. Now let's explore each term of this equation. First, the inertia term. The first two terms of the momentum equation constitute the inertial forces. These terms describe the resistance of the fluid mass to changes in motion. The first term, called local acceleration, represents the temporal change in velocity at a fixed point in space. It is the definition of unsteadiness and is dominant when flow conditions change rapidly over time, such as during sluice gate operation, pump startup, or the immediate aftermath of a dam break. Retaining this term allows the model to simulate the time lag of the wave response. The second term is called convective acceleration and represents the spatial change in velocity. It accounts for the acceleration or deceleration of fluid particles as they move through spatially varying geometries. This term is critical in non-prismatic channels where width or depth varies, such as at bridge constrictions or at transitions between mild and steep slopes. It represents the kinetic energy conversion. Neglecting this term removes the ability to model backwater effects resulting from changes in the channel geometry. In the context of the Freud number, this term becomes significant as Freud approaches unity or critical flow condition. The remaining three terms of the momentum equation represent the external forces acting on the fluid body. First is the pressure gradient. This term represents the longitudinal gradient of the hydrostatic pressure force. This is the primary mechanism for wave diffusion or attenuation. In subcritical flow, this term allows information to propagate upstream. Neglecting this term results in a pure translation model that cannot simulate the subsidence of a flood peak. The second is the gravity force. Represented by a snot or bed slope, it is the component of gravitational acceleration acting in the direction of the flow. This term is always retained. In the absence of other forces, gravity accelerates the flow until balanced by friction. The last one is friction force. This term represents the resistance shear force at the bed and banks. It dissipates energy and is typically defined by Manning's equation. Models that simplify this term typically cannot handle flow reversal, such as tidal cycles or storm surge. By keeping the continuity equation in its full form and selectively neglecting terms in the momentum equation, engineers have derived three primary classes of hydraulic models. Now let's go through the hierarchy of hydraulic wave models. First is the kinematic wave model. This is the most severe simplifications of the Saint-Venant equations. It neglects all inertia and pressure terms. In other words, it assumes a balance strictly between gravity and friction forces. The discharge Q becomes a single-valued function of cross-sectional area A, typically expressed as this. Substituting this into the continuity equation yields the kinematic wave equation. Here, Ck is the kinematic wave celerity defined by this. The characteristics of this model are as follows. First, pure translation. It means the flood wave translates downstream without physical attenuation. Second is the kinematic shock. Because the wave celerity Ck increases with depth, higher parts of the wave travel faster than the lower parts. This leads to wave steepening, where the crest overtakes the trough, eventually forming a vertical wall of water known as kinematic shock. This is a physical instability inherent to the model. The third is the no backwater. Since the pressure gradient terms partial of y with respect to x is neglected, the kinematic wave model cannot simulate backwater effects. Lastly, validity for a steep slope. The kinematic wave model is valid for steep slopes and overland flow where gravity forces dominate pressure and inertia. The diffusion wave model, also known as the zero inertia or non-inertia model, improves upon the kinematic wave model by retaining the pressure gradient term while still neglecting the inertia terms. The momentum equation simplifies to this. Therefore, the friction slope differs from the bed slope due to the slope of the water surface. Substituting this into the continuity equation gives an advection diffusion equation like this. The characteristics of this model are as follows. First, the physical attenuation. Unlike the kinematic wave model, the diffusion wave model simulates the subsidence or flattening of the flood wave peak as it travels. Second is the partial backwater. The inclusion of partial y with respect to x allows the simulation of backwater effects. A downstream boundary condition can propagate information upstream, influencing the water surface profile. It cannot accurately model high inertia events like sudden gate closure or the immediate shock of a dam break. It also typically cannot simulate flow reversal. Finally, the dynamic wave model. This model retains all terms in the Saint-Venant equations. This model is essential when the inertial forces are comparable to gravity and friction. This occurs in rapid transients like dam breaks, tidal flows when boundary pressure drives the flow against gravity, and networks with closed loops. Use the table below to compare the capabilities of these models. This comparison is vital for engineers to select the appropriate tool for a given problem, balancing accuracy with computational cost. Thanks for watching. If you have made it this far, you're exactly the kind of curious and thoughtful viewer we are here for at Water Edu Hub. More videos are on the way. Stay tuned.